Video 62 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is excited determinants and excitation operators. In the beginning of chapter 9, we discussed that our approximations to the unperturbed electronic wave functions will be a linear combination of Slater determinants. In the last chapter about Hartree-Fock theory, we met the Hartree-Fock-Slater determinant, the one where the spin orbitals in the Slater determinant are the spin orbitals, the n spin orbitals for an electron wave function with the lowest orbital energies. In this chapter now we want to discuss how to generate more Slater determinants, which we then can use in this linear combination, which forms the approximation to our ground state wave function. In principle, this is quite easy because by solving the Hartree-Fock equations, we obtain many more spin orbitals as the n spin orbitals which we need to use for the Hartree-Fock wave function. When we expand the spin orbitals, the solutions to the Hartree-Fock equation in a set of atomic orbitals or basis functions, let's assume we have m basis functions, then of course we will also obtain m solutions to the Hartree-Fock equations, which means we will obtain m spin orbitals. From those m spin orbitals, we need the n spin orbitals with the lowest energy for the Hartree-Fock determinant. We call them the occupied orbitals, which means that there are m minus n unoccupied or virtual orbitals left, which we haven't used then. So from these virtual orbitals, we can make many more Slater determinants. Now, normally, in order to keep some order in this relative large set of spin orbitals, one tries to relate these other determinants to the Hartree-Fock determinant. And one does this by specifying how many of the occupied orbitals have been replaced in the Hartree-Fock determinant to obtain this new determinant. For example, if one replaces one occupied orbital I by an unoccupied orbital A, one calls these determinants singly excited determinant, and we try to identify this by writing I here below and A above. So I was replaced by A. Correspondingly, if one replaces two occupied orbitals I and J by two virtual orbitals A and B, where I was replaced by A and J was replaced by B, then one calls this kind of determinant a doubly excited determinant, and so forth, which means one ends up with determinants which can at maximum be n-tuply excited, where n is the number of electrons in the system and therefore the number of spin orbitals which we have in our determinants. Personally, I think calling them excited determinants are rather unfortunate because a priori these determinants do not have anything to do with excited states of the system. They're just additional determinants in our set of many electron wave functions, which we also can call the many electron basis functions, which we use to approximate the exact unperturbed wave function. However, there are very approximate methods where, for example, a single such singly excited determinant can be used as a very, very crude approximation to an excited state. In the following equations, it will be actually very convenient to make this relation between these excited determinants and the Hartree-Fock determinant very explicit. Meaning we introduce now some operators which turn the Hartree-Fock determinant in one of these excited determinants, which means it will carry out this excitation, or I would like to say, which carries out the replacement of occupied orbitals by virtual orbitals. And we call them excitation operators, and I use this symbol H for them. And E is supposed to indicate that it's an excitation operator. And the I indicates how many orbitals are replaced, which mean the excitation levels. So it would be singly, doubly, triply, and so forth. And the mu is just the index for identifying the particular excitation which has to be carried out. And sometimes we will denote the whole set of these operators, which you can put in a vector. So we collect them in a column vector and identify them then by the bold H identifying that this is a vector. Alternative, in some cases, one will, instead of using the symbol H, we will write these excitation operators up in form of single excitation or orbital rotation operators, as they're also called, and use the symbol Q for that, Q dagger for the excitation operator, where I and A are the indices of the orbital. So the Q dagger IA operator replaces the occupied orbital I by a virtual orbital A in whatever determinant it acts on. Which means we can write a single excited determinant where the occupied orbital I was replaced by a virtual orbital A as the Hartree-Fock determinant on which we act with this orbital rotation or single excitation operator Q dagger AI, or as an example for one of these general excitation operator, but excitation level 1, so it's a single excitation operator. Correspondingly, we can write a double excited determinant IJAB as the Hartree-Fock determinant on which we act now with a product of two orbital rotation or single excitation operators, or we act on it with this general double excitation level 2 operator. That means that our expansion of our wave function as a linear combination of a lot of different determinants, basically all determinants which we can generate, we can actually write in this way here, where we have the Hartree-Fock determinant, and then we have different operators acting on them, one, and then this T1 operator, a T2 operator, up to Tn, where n is the number of electrons in the system. And these capital T operators, they actually are the sum of all operators of this excitation level. So the T1 operator is the sum over all single excitation operators multiplied with some coefficients already. So it's a weighted sum of these operators, where here are the coefficients, and these coefficients, depending on what kind of method we are going to look at, have different names. They will sometimes they will be called correlation coefficients, sometimes they will be called amplitudes, and sometimes I just call them coefficients. So a T1 is the sum of all possible single excitation operators weighted with these coefficients. T2 is the unique sum of all double excitation operators weighted with double excitation coefficients, double amplitudes, or double correlation coefficients. And in general, we have a TI operator, which is the sum of all excitation operators of excitation level I, weighted with their coefficients. And here we have the n-tuple operator, then of course would be the sum of all the n-tuple excitation operators with their coefficients. And if a T1, for example, now this T1 operator acts on the Hartree-Fock determinant, then we get a sum of all single excited determinants weighted with these amplitudes or coefficients, because it's the T1 is the Hartree-Fock determinant on which we act with this single excitation operator, which then generates the single excited determinants. So with these different operators, either the capital T operators for having a sum of all excitation operators of a particular level, or the individual operators, we can generate from the Hartree-Fock determinant then excited determinants in the ket. Correspondingly, we would like to do that now also for a Bra wave function. And we can write this in a similar way as we did it for the ket wave function here, as having the Hartree-Fock Bra wave function and then acting a series of operators on it. Now we should remember that, of course, we can let an operator act also from the right on a wave function in a Bra. That means that the operator is moved in here. For example, this lambda1 operator is then moved in here in front of the wave function, but it's not lambda1 which then is going to act on the Hartree-Fock, but it's the adjoint of lambda1. So it's lambda1 adjoint, which means that the adjoint of lambda 1, if I want to generate excited determinants, then the adjoint of lambda 1 has to be an excitation operator. And that means then that lambda 1 itself is actually a de-excitation operator. Because lambda 1 and all the other one lambdas also here are then the adjoints of excitation operators. And as you can see here, the adjoint of an excitation operator is then going to be a de-excitation operator. So lambda 1, lambda 2, lambda I up to the n tuple are in a way the corresponding de-excitation operators to the capital T operators here. So they are a linear combination of single de-excitation operators, double de-excitation operators, or general I tuple or n tuple de-excitation operators weighted with some coefficients. And those coefficients lambda here, which are just basically just normally called the lambda amplitudes, they are a priori not related to the T amplitudes, so they are different. Different amplitudes, different coefficients. So the lambda are de-excitation operators, and I can illustrate the effect of these H operators here, the H D indicating de-excitation operator, because if one lets act one of them on a SDF wave function in the bra, one gets a single excitation operator, which was a single de-excitation level, and if it's a double de-excitation level, if we let it act on a Hartree-Fock wave function in the bra, we get actually a double excited determinant in the bra. The final thing which we are going to need later on is that the whole set of these excitation operators, actually excitation and de-excitation operators, actually forms a complete set of operators, meaning that one can use it as the resolution of the identity. So one actually can be written as this projection operator with the Hartree-Fock wave function, and then a sum over all the projection operators, including the excited determinants, which we of course we can generate in the ket by using the excitation operator, and the bra we can generate them by using the de-excitation operators.